Hello and welcome to my channel again. Today's video's topic will be accidental degeneracy of hydrogen atom. Now I will explain everything, that what is accidental, why it is accidental, what is degeneracy and all. Now I will assume that you also have some kind of idea about symmetry and why symmetry exists and all, because this is a master level video, so I think I can assume that without any harm. Now let us consider hydrogen atom. Okay, we all have solved for hydrogen atom energy eigenfunctions and energy eigenvalues, stationary states. Now, if you see the particular eigenvalue of the hydrogen atom, you will see that without any correction and all, there is no L or any other quantum number dependence on the energy eigenvalue. Now, if you see, to specify the particular quantum states, like to label them, we have particular complete set of commuting operators like L squared, Lz, and the Hamiltonian itself. So all of them are commuting operators. So we have N, L, and Ml. But the point is, we have L, Ml, but they are not contributing to the energy. So if they are changing, the state changes, but the energy remains the same. So we can say that there is a degeneracy existing. So multiple states present in a single energy state can be referred as degeneracy of the quantum system. Degeneracy is always a quantum phenomena. It has no classical fingerprint or classical print at all. So I want you to remember that. Now we can say that the ML degeneracy is associated with the rotational symmetry of this hydrogen atom system, or the central potential. Okay, because we know that the hydrogen atom is basically a result of Coulombic potential. Okay, the electron and the nucleus of the hydrogen atom basically interacts via a Coulombic potential. Here in today's video I will show that the particular Coulombic nature is necessary to exist for existence of the accidental degeneracy, otherwise it won't hold. We will go into the mathematics, but here I want to specify that if we look for the L values, like we have n minus 1 L values for a given given n. Now why this L exists in a degeneracy factor, or why the L is contributing to our degeneracy factor? This is the question, because the existence of ML can be explained by the rotational symmetry of the system, SO3 symmetry of the system. The SO3 symmetry exists, we all know, because of the central potential. Now I will just go back to my board, erase it, and start with the derivation and explain all of the small minor details that is present in the derivation. Okay, so as you have seen, I have erased the board and I have written the energy eigenvalue there. So let me just read it for you, which says that En is equals to minus 1 by n squared, and then this quantity, which basically will reduce to 13.6 electron volts. Now here I want to mention that you will see only n principal quantum number is present here in the energy eigenvalue, but when we denote quantum state of hydrogen atom, we will write NLM. L, you can say. So we have only energy dependence upon this principal quantum number, but there is no dependence on L and Ml, as I said. Okay, Ml is degenerate due to rotational symmetry. It's a 3 rotational symmetry because it has a central nature of the potential. It is a central force potential, right? And the central force potential is always SO3. Okay. So basically, this is the reason why ML degeneracy exists. But what about L? Okay, I know I am repeating myself, but you should understand it very carefully. It is a very important concept. Many people get confused over there, so that's why I am making it a little bit of visual representation. The first one was a verbal, this is a visual. Okay, so what is the reason that I have n L going to n minus 1 number of values? The energy remains unchanged, but the state changes, but there is a degeneracy. What is the associated symmetry with it? We are asking this following question. Okay, what is the symmetry associated with it? So accidental degeneracy will have some kind of a dynamical symmetry. Okay, now here, if we want to use the term dynamical symmetry, we have to mention then what was this SO3 symmetry. Okay, so SO3 is basically a space-time symmetry. Okay, I will write over there later. So SO3 is basically a space-time symmetry. Space-time symmetry means the transformation we are giving. The symmetry means what? Symmetry means what? If I have some quantity x and I transform the certain quantity to x prime, I am not saying x as a position. Okay, I am saying x is a random quantity. It can be anything. And if you get confused, let me write it the alpha. Okay, so alpha is going to alpha prime, and now I want to understand that under this certain transformation, if my system is invariant or not. Okay, now this transformation can be a space-time transformation. This can be in any other type of transformation that exists. Okay, I will not go into that much detail, but the point I am trying to make is basically that alpha is going to alpha prime. Okay, via some kind of a transformation. I am applying a transformation to my system, and under that transformation, if my system remains invariant, I will say there is a symmetry. And if the transformation is basically a type, the type of space-time transformation. Okay, and that means the operator which is acting on certain quantity to transform is dependent upon the space-time coordinates. Okay, this is a space-time symmetry. But in the case of dynamical symmetry, why it is dynamical? Because it has no noise current associated with it. Okay, it has no noise current associated with it, and the symmetry lies on the equation of motion. This is the very important part of the whole thing I am going to do. Oh, I also forgot to mention on the first part, like this video or this thing will be like separated into 3 portions. Okay, I will in today's video only perform the evaluate the conserved quantity which is conserved, and after on the next video I will show that Coulombic nature is necessary for existence of this kind of a degeneracy. If the Coulomb nature goes away, then you will not find this accidental degeneracy. Okay, I will use the simplest violation of Coulombic nature of the potential, which is 1 by r square. I will apply 1 by r square, and you will see that the conserved quantity do not exist. And after that I will prove two quantities which are basically given to the students as homework, and it is very difficult. Trust me, I've tried a long time to solve that. Okay, they just give that randomly to the exam, and the students usually don't know how to do that, so the marks are lost. I will help them in this video. So there will be 3 parts. On second part, I will do the Coulombic dependence of the accidental degeneracy and the first proof, and on the next video I will take longer time to do the second proof because it is very long. Okay, it is very elongated, like it will take at least 30 to 40 minutes. Now let me go to the equation part. This is all explanation is done. So all we have understood till now is that SO3 which exists in ML is a space-time symmetry, and the existence of degeneracy in L will be due to the dynamical symmetry, which is the degeneracy or which is the symmetry which is existing on the equation of motion, not in the space-time. Okay, this is due to the space, not due to the space-time transformation. I will just write it as dynamical symmetry. Okay. I will write a bit of statement that will help you. If we have a particular conserved quantity specified by a particular Hamiltonian, I am writing H, okay, particular Hamiltonian, and that conserved quantity can only be defined or found via the equation of motion of the system. Then it's called the dynamical symmetry. Okay? The potential for the hydrogen atom problem is, it is basically V of R is equals to minus Z squared by R, we know that, and the force due to this potential will be minus del V del F, we know, okay, or minus grad V, okay. So it will be minus, I will replace this Z square with a K, okay, K by R square, R cap. So this can be written as, this R cap will be R vector by R. So K by R cube R vector. Okay, this is my force. Now from the second law of Newton. Okay. Now a problem or a doubt can occur in your mind that this is a quantum mechanical problem, right? Why you are using the Newton's law and potential and this classical equation of force? We should have used the Heisenberg equation of motion, right? But listen, the problem is not quantum mechanical at all when you are talking about dynamical symmetry. Okay, we can just take the whole problem to be classical, then rank them up by just adding an operator status to it. Okay, like we can evaluate the whole thing in classical space, and then we can just add an operator status to them and add the hermiticity nature for the real eigenvalue. Okay, and then the whole thing can act as a quantum thing. It will not break any quantum laws, or it will not affect our system's results. Okay, so if that doubt occurs in your mind, so this is a good doubt in some sense. So now from the second law of motion, we can Newton's law, that m r double dot is basically minus k by r cube r vector. Okay. Now okay, let me give it equation 2 then. I have given already one here, and this is equation 3. Okay. Now taking cross product on both sides of 3 with L by M, and L is basically the classical angular momentum, okay, orbital angular momentum. So I will see that the M will get cancelled out, and R double dot cross L plus K by R cube R cross L. Okay. Now in a central force system, we know that angular momentum is conserved, so dLdt is 0. Okay. I think you know this. This is the BSc level central force part concept I am using. So if I say that my dLdt is 0, so I can write this whole thing to be ddt of R dot cross L. I think you guys will agree with me in this case. And L is equals to also R cross P. Okay. R cross P is basically R cross M equal to M R cross R dot. Okay. R dot means the velocity, and I am taking the M out, so I can cancel out. Okay. It has M here. I forgot to write. Plus K by M R cube R cross R dot. Okay, with the M, and that is equals to 0. Now you will see that this is basically A dot B cross C, A cross B cross C. So A cross B cross C can be written as BAC minus CAB. Okay, back cab, I like to say it. From Griffiths I have learned that. So ddt of R dot cross L plus K by R cube into BAC back minus cab CA. Now R dot R can be written as R square, but we will write that later. Okay. I think the dots are visible. Okay, please. If you have any problem, please comment down. I will clarify. Okay. But I think you guys can understand. Okay, that much. Now we will just talk about the second term individually, because we have done it. This part is 0. So now if we take the integration over dt, I will get my conserved quantity for this part. But this part is also not done yet. So I have to now simplify this only the second term, because this part is done. This part is done. Now if we take the 1 by R cube over there, we will get, this is R squared by R cube, so basically R dot by R minus R dot R with the R by R cube. This is where we want to reach. Okay, this is where I want to reach. So let us take a quantity. Now this part requires a knowledge of mathematics, because how will you know that you have to take this particular quantity, okay, this particular quantity to receive on that particular point. Okay, this is the mathematical marvel we need to study physics. Now if we take the derivative out here, we will find that R dot with mod R minus R with ddt of this Okay, I'm adding a mod just to make things look good. Okay, and from here the r and r square will get cancelled up, so I will end up with r dot by r. Okay, you can see that this term is already here, minus r by mod r squared, then ddt of mod r. Okay, I think I have done everything right. The 1 by r and r thing, r and sorry, this is the r vector. Okay, please, this is r vector, do remind that. And this r dot also have a vector sign over there. Yes, this r dot also have a vector sign over there. Vector signs are important. Okay, don't miss them. Now from here we can say that my mod r is equals to r dot r. So ddt of mod r will be r dot r by mod r. Okay, this is the derivative dot, this is the normal dot. Okay, so ddt of r by mod r is basically equals to, we have ended up with this and this. Okay, here I have used the fact that this thing by putting here, okay, this thing I have inserted here, vector, okay, fine. So my final expression will be, I am not sure if that much low is visible or not, so I will just go over there and erase the board. I will erase the board and welcome to the last segment of our video. So here I will write that ddt of this thing, okay, r dot cross L plus I have a k here, then the whole thing, so r by r cube. Okay, sorry, not r cube, extremely sorry, this is model, this model. Okay, this expression I need to insert. This is 0. I think last I used equation 3, so this is equation 4. Okay, now integrating equation 4, you can do all of that mathematical nonsense. I am not interested. So finally I will end up with r dot cross L, r dot cross L plus kr by mod r, this whole thing equal to constant. Okay, I can add a m here divided by a m here. Okay, so this whole thing will be p cross L by m plus kr vector by mod r. Let us say this constant is some kind of a curly r. Okay, I am writing it like this. Okay, curly r. Now this whole expression is classical. Okay, so I am putting just a vector over there. This thing in classical mechanics and also in quantum mechanics is called Rungi-Lenz vector. Okay. So what is the conserved quantity in dynamical symmetry? We will consider that as a Runge-Lenz vector. Okay. Now in the case of Runge-Lenz vector, this is classical quantity, right? This is classical. So to make it a quantum operator, we must incorporate the idea of hermiticity. Okay. So we will just write P cross L with operator status on them. I don't know if it is too small. P cross L with operator status, okay, minus L cross P. I have now allowed the non-commuting nature as their operators, okay, divided by 2m, okay, and this part is basically a scalar quantity, so I don't have to too much worry about that. Not scalar, but it is a directional quantity and it does not matter to us. And this will be our Runge-Lenz vector. Okay. This is our quantum mechanical Runge-Lenz vector. I think you have understood the thing, what I am trying to say here. I will sum up as we had our Lagrangian, Hamiltonian, both for the hydrogen atom system. We will work with Hamiltonian quantum mechanics, and in the case of energy eigenvalue, we have already seen that there is a degeneracy which exists in both L and ML. The degeneracy of ML can be explained by the rotational symmetry of the central potential, but the degeneracy in L cannot be described. Okay, degeneracy L cannot be described. So we have said that the degeneracy L do exist due to the dynamical symmetry, not the space-time symmetry, as SO3 is a space-time symmetry. Okay, in the next video I will also explain that how this is related to SO4 symmetry. Okay, I'm not introducing that SO4 symmetry today because I will give you guys a little bit of time to practice all of this thing before we move to that much of advanced topic. Okay, I will on the next video do the SO4 thing, and then I will prove that if you take a particular shape of potential which is non-Coulombic, the whole thing just blows up. And then we will also prove for certain quantity which I have to show to 0 and that is related to that SO4 symmetry also. Okay, so I think you have understood the problem. Not the problem but this is the derivation. Okay, so I have understood the derivation, and thank you for watching. Please if you like the video, do like it, and if you have anything to comment, anything you have need to ask me, you can always comment down, and if you are new, do consider subscribing because you're already here. Okay, thank you.